Ladies and gentlemen, welcome to the fabulous room 1065. It's the Kelvin Dueck Physics Show Extravaganza. Here's your host, the king of acceleration. It's Kelvin Dueck.
The king of acceleration? Okay. Here we go. In physics, you learned last year in Science 10, in theory, every measured quantity is either a vector or a scalar. And this year, you'll start to see why it is important that you know the difference. It'll be one of the few times when I say, you want to memorize this. Anytime I show you a new concept or a new unit or a new idea, I'll say to you right away, vector or scalar. We'll write down what it is. Because there are different rules of math for vectors than there are for scalars. There's a whole branch of vector mathematics that you'll start to learn this year that you'll really get into in Physics 12, those of you that take it next year. Scalars have magnitude only. Magnitude is a fancy word for size. As an example, 6.3 kilograms. Mass has no direction. It just is. As an example, 32 milliliters. Volume has no direction, it just is. Some of the stuff we'll be looking at this year, 8 meters per second, that's a speed. The magnitude is 8, but have I told you which way they're going? It's a scalar. And 3.2 meters. That has a magnitude of 3.2 meters. Is there a direction attached to that? No. That's a distance. Vectors have both, the phrase we flog to death is magnitude and direction. My first two are going to be the last two from the scalar. I'm going to say, oh, how about 8 meters per second due north? Magnitude and direction. Oh, you want to get really intent, very specific on a direction? How about 3.2 meters at, that's an at symbol. I know I have trouble drawing that, but that's an at symbol. 40 degrees north of east. That's a direction. Mr. Dueck, what would that look like? We'll actually learn how to do stuff like that in our vector unit, which will be somewhere around April or May. But for what it's worth, as I cough, Emma, can you read this after the at to me, please, out loud? Say it again, out loud. You're right. North of what? North of what? I'm doing this for a reason. North of what? If you were drawing this, you would go east first as a dotted line. Don't draw this, I'm just showing you. What of east? What of east?
North.
North of east, you'll go north. How many degrees north? That would be a line that would be about 40 degrees. It would look kind of like that. That's 40 degrees north of east, roughly, give or take. I need a protractor to do it properly. But we'll learn that we can get any angle on the compass that you want me to get by saying south of west, north of east, east of north, whatever you need us to get, we can draw it. And you draw the of first as a dotted line, and then you do the thing in front of the of as that's which direction you're going to go, how many degrees. There are other things, the other quantities that you'll learn this year that are vectors. Momentum is a vector, force is a vector, acceleration is a vector, energy is a scalar, work is a scalar. Blah, blah, blah. That's the big ones we'll look at this year, and then you'll learn a whole bunch more next year. So we have scalars and vectors. Oh, here's some examples. So, scalar, 30 kilometers per hour. That's a speed. Vector, 30 kilometers per hour at 29 degrees west of south. That's a vector. How would I draw that, Mr. Dueck? You don't need to know this yet, but Tawny, can you read to me what it says after the at symbol?
29 degrees
West of what? West of what? You would go south first, like that. Which way would west of that be, left or right? How many degrees? 29? You know what? It looks something like that, kind of. Preview of coming attractions. Scalar would be 12 meters. Vector would be 12 meters due north. Scalar could be an acceleration of 5.5 meters per second squared. That's a 2. Acceleration is kind of a weird one. Who remembers what we call this first thing here? If it's a scalar and it's how fast, what word did we use in Science 10? Began with the letter S. Speed. If it's a scalar, if it's a vector and how fast, what word did we use? Began with the letter velocity. Okay, we have two separate words. If it's a how far scalar, what word did we use in Science 10? Began with the letter D. Distance. If it was a how far vector, what word did we use in Science 10? Also began with the letter D. Displacement. Acceleration is the weird one, because if I say find the acceleration, often I mean just the magnitude, like that. There is no other word, there is no vector word for acceleration, but I can tell you if I said this, I think that negative suggests we're slowing down, and that gives me a direction. Okay. There's lots more, but these are the ones we're going to be looking at the most. Little note, if you ever have a physics textbook, and I'm not a big fan of the current physics textbook, so I've typed up my own for you, but in a textbook, vectors are written in bold font, but it's really, really hard to handwrite a bold font. It just looks kind of stupid. So the other way that we write them is we put a vector arrow. Speed, velocity, although over the years we've gotten lazy, and instead of a full arrow, it's often just kind of evolved into a half arrow on the top. Distance, displacement, acceleration, well, acceleration, but I'd probably be looking for a direction there. Sorry, don't have a separate name for that one. Not as far as I know anyways. Okay. Someone's phone, at least it's on vibrate, but they're not that important. They can power it off surreptitiously. Can't they? No. Timbit says when there's noise, vibrate I'll live with. So, distance versus displacement. Distance is just how far an object has traveled. Symbol? D is actually wrong. I'm going to give you the correct symbol. Then we're going to cross it out, and I'll tell you why we don't use it unless we're in Britain, but it is the correct symbol. Then I'm going to give you the second most correct symbol. I'm going to cross that out, and we're going to settle on D because it's easy to remember. But the correct symbol for distance, believe it or not, is the letter lowercase s. From Latin, in case you're wondering. I think Latin summa, but don't quote me on that. The problem is, first of all, what units have a lowercase s? Seconds, and we use time an awful lot. And also, what number does that look like if I don't write it really, really, really carefully? A 5. So you know what? I'm not going to use that one. You may see that, especially if you look at a British physics textbook. It is actually the correct one. The next one they often use is x because you're talking about a graph, you're talking about the x-axis, and so they'll say, oh, positive x is to the right, negative x is to the left. It works really well. Yeah, I kind of like that one, and I may pull that one out once in a while, but not that often. We are going to use d for distance. Who's in grade 11 here? Those of you that take calculus next year, and some of you will, you're going to find the other reason D is bad is the letter D means something hugely fundamentally important in calculus. It means you're taking the derivative, which is, there's two branches of calculus, integration and derivatives. And it's hugely important, and so you shouldn't use D as your symbol for distance. So in calculus, you almost always do use X. We're in Physics 11. D is easy to keep track of. Fair enough. Units, meters. There are other ways to measure it, but we're going to do all of our math, all of our equations in meters, and if it's not in meters, we'll do a conversion. The two most common will be centimeters and kilometers. Hopefully you know enough to maybe even do those in your head. Hey, 2 kilometers is 2,000 meters. You can do the chain if you need to, though. Displacement is an object's change in position. Technically, the correct symbol, not going to use that. Probably a better symbol, not going to use that. We're going to use that. Why? Because D for displacement, and I don't want to stretch your brains too much. What do we mean by the difference between the two? I need a volunteer. Oh, so one of our standard fallbacks is we like to visualize little bugs walking. So a bug walks along a number line. It starts at A, walks to B, and then turns around and walks to C. If I was drawing that, it would look something like this. Starts at A, walks to B, and then turns around and walks to C. And sometimes the picture helps me really visualize what's going on. I think that picture, that little drawing does. What distance did the bug walk? Let's see. 4 plus 10. Now, if you just wrote 14, I'd be fine. In our notes, let's write down our reasoning so that when we're studying, we know what the heck we did. 14 meters. I don't care left or right. I don't care direction. Magnitude only. Ah. What's the bug's change in position? What's the negatives telling you? To the left. There's our direction. We're going to decide most of the time this year, Reed, that left is negative, right is positive, up is positive, down is negative. Not always. There's going to be some times when it's so much more convenient to let down be positive, because that's what we're interested in. We'll just do that, and we'll just say, it'll be positive for the remainder of this question. Not that big a deal, because it's completely relative. You can do whatever you want. You could let to the right be negative and to the left be positive. But when in doubt, positive, negative, positive, negative, when in doubt. Speed versus velocity. Average speed, scalar or vector? So it's going to be a scalar divided by a scalar. It's going to be average speed, is the change in distance, not change in displacement, change in distance over time, where delta means change in. I don't memorize that equation. I memorize, in fact, I don't memorize this equation either, but this is one we're going to use. What's our symbol for speed? Not S. V for speed. Well, for velocity, but yeah. So speed equals distance over time. Remember I said to you that we get sloppy, that because time is always a change in, we stop writing the change in because you can't measure time without starting and stopping a stopwatch, and we kind of do that for distance too. What would the units be? What do I measure distance in? Meters. What do I measure time in? So are you saying the units would be meters over second, meters per second, and it's a scalar? Average velocity is displacement over time, where that triangle does still mean change in. As an equation, it's exactly the same as we've written, except that's a vector, that's a vector. Why didn't I put a vector symbol over time? Time is always a scalar. Time has no direction. Well, I saw this video once where they went backwards in time. No, time is always a scalar. Time has no direction. It just is. Yeah.
Mr. Dueck, where it says average velocity, where we represent the t for time, wouldn't there be a delta symbol there too?
Yeah, but I'm so lazy I don't even think about putting. Good point, but I've long since turned that part off in my brain. Good point. Units still meters per second, but this is a vector. Okay. Example 2. Suppose the bugs trip mentioned in example 1 took 2 hours. What's the bug's average speed in meters per second? Meters per what?
Second.
How much time did they give me in this question?
2
Hours. I'm not going to do that. Let's do a conversion. Over here, t equals 2h. Can I go from hours to seconds?
Yes.
Oh, some of you have memorized the... How many seconds are there in 1 hour?
3,600.
Okay, it's 60 times 60. If you need to build the minutes to seconds chain, go right ahead. But since some people seem to have memorized that, and I'm not testing your ability to convert, hours would go on the bottom, seconds on the top, 3,600. Oh, you know what? I'm pretty sure time is 7,200 seconds. So that's what I'm going to use. Got my units correct. Average speed is just distance over time. What did we say the bug's distance traveled was on the previous page? 14 divided by 7,200. By the way, for what it's worth, how many sig figs does that 14 have? 2. How many sig figs does the 7,200 have? 2. How many sig figs will my final answer be? 2. And again, I'm not enforcing sig figs for the remainder of the year, but I'll keep flogging it to death. This is going to be something pretty small, I imagine. (1.9) 2 sig figs times 10 to the negative what? 1, 2, negative 3, right there. Not going real fast. That there would be 1 centimeter per second. This right here is in millimeters, so it's going almost 2 millimeters every second. Just slightly slower than that. It's a bug. Didn't say it was not a beetle. Could be a slug. Could be a snail. What's the bug's average velocity? Well, average velocity is going to be displacement over time. What was the displacement?
-6.
-6 over 7,200. And I get -8.3 times 10 to the -4. Or you could say 8.3 times 10 to the negative 4 meters per second to the direction. What's the negative telling you? To the left. Which one of those is less writing? Putting a negative or writing out the phrase to the left? So let's use that first one. But for what it's worth, that's what it implies. You can go with that other one if you want to. I'll read it and I'll notice that, but be lazy. Okay. I'm a big fan of Foxtrot comics. Any of you read Foxtrot comics? Ben? Okay. The author, Bill Ammond, the reason I like it so much, he actually has a physics degree. And in fact, while he was doing his undergrad in physics, he was often doodling in his notebooks, and some of his friends said, "These are funny. You should try and publish these." So he's a full-time comic strip artist. But the math and the physics that he pulls out is correct. He's also a bit of a nerd. In fact, the character that I identify with is the youngest brother named Jason. He's the uber nerd. His older brother is named Peter, and Jason is giving Peter a football play to run. Says, okay, here's the play. Go 40 yards downfield, then turn left and go 20 yards, then turn right and go 25 yards, then turn right again and go 30 yards, then turn right and go 30 yards, then turn left and go 10 yards, then turn left and go 15 yards, then turn left and go 20 yards, then turn left and go 50 yards, and I'll hit you with the ball. Peter thinks for a moment. Won't I be right back where I started? Jason says, oh, I can't throw very far. So here's the new play. I never get to be quarterback. We have actually run this play out on the field, and you do end up back where you started from. We did double check it one time. And I'm tempted to do that right now, but it was a little wet out there. We had a downpour at lunch, so we're not going to try running it this time. First question. What distance will Peter run in order to complete this play? Well, how far is he running on the first stretch? Because distance doesn't care about direction. How far is he running on the first stretch? Then what? 20. Then what? 25. Then 30. Then 30. Then 10. Then 15. Then 20. Then 50. What do you get? And instead of yards, let's make it meters just so our units match. It's close. How far will Peter run? Can I do this in my head? 40 and 20 is 60, 85, 115, 145, 155, 160, 170, 190, 240?
Yes.
Woohoo! All right, let's put yards. We'll make the Americans happy with their stupid imperial system. Okay. What's his displacement? 0. If I timed how long it took to run this play, we could find his average speed by going 240 divided by however long it took. It would take a while. But his average velocity would be 0, because it would be 0 divided by the time. Is that all right? Nice yawn? Nothing there? I got Jeff. I missed you. My aim was a little bad. Homework, it says. Say what? I'll show you. Okay. It says distance versus displacement and speed versus velocity. Below is a map of a happy country that lies deep within the subconscious of crazy physicists. When they feel stressed out or sad, they go to this happy little country and they ponder kinematics problems as they travel from one happy town to the next. Oh, what a great place. It makes them happy, and I know it will make you happy too. It's a happy little town with a happy... How many of you watched on PBS the big Afro painter guy that does the happy little... Bob Ross, right? Now we're going to draw a happy little tree, and over here, let's put a little happy little cabin. And how about a happy little boat? He's great relaxing to watch when he's doing it for, So here's what we have. We have 1, 2, 3, 4, 5, 6 different towns, and what's the scale that I've put on this map? So if you want to find a displacement, you'll physically measure with your ruler, and your number will be totally different from mine because mine is like really wide because of the screen distortion. And if you multiply the centimeters by 10 kilometers, that's the displacement. If you want to measure the distance, you can't because it's curvy roads. Oh, did I tell you the road distances down here? I did? Okay. So on the next page, for example, I said you'll need a ruler with centimeters. For each of these, I want you to find the following. I don't know if you have room. No, you don't have room to answer them on this page. Answer them on a separate page. So you're going to find 4 things. The distance traveled in kilometers. The magnitude of the displacement measured with a ruler in kilometers. The average speed, which is going to be distance divided by time. And I think I tell you in the question how much time. We're going to use kilometers per hour instead of meters per second. Oh, and the magnitude of the average velocity. You can't give me a direction because I didn't put compass angles or anything on here, but you can give me the magnitude of the average velocity. Give all answers to the correct number of sig figs. Assume your rulers are accurate to the nearest millimeter, which means I think you can go 1.2 centimeters, 1.3 centimeters, so you'll be able to go to 1 decimal place, which will mean that you'll be going to 2 or 3 sig figs, depending on the question. Okay? Any questions at all here? Does that make sense, what we're getting at?
Yeah.
So you have 1, 2, 3, 4, 5 questions, 20 calculations for each one. To be honest, most of you will be done by about 1 p.m. If you finish it in class, check your answers to make sure you did it right, and then you can hand it in back there. But I'm not going to go any further today.